Okay, hello everyone. Welcome back to the DOTS lectures. So we were right in the middle of a discussion, and I'm going to pick up right from there. So last time what we were doing is we're working our way towards this general representability theorem in 2 algebra, um, and with the express intent of getting towards the compositionality of representable behaviors of dynamical systems of all the various sorts we've sort of covered and more that we haven't covered but really should, which I will, I think, duly go into after this. I'll go and run through the consequences of this theorem in a number of different examples. But for now, we are we are sort of really stuck with our heads way over the clouds, and we're doing 2 categorical algebra. So what I was talking about before is what the 2 category of algebras of a 2-monad. So a 2-monad is something like this T that I put up here, which was the free symmetric monodal category 2-monad, and a 2-monad may be on other 2 categories, as we discussed in my lead up to this in the last lecture. We're going to be looking at a 2-monad on this 2 category of these diagrams of categories, which is the underlying data involved in a systems theory, more symmetric monodal loose right modules of systems. But if we take the free symmetric monodal category, we also need to understand this category of algebras. And an algebra homomorphism is something like this. At least that's what you would naively expect if you took the 1 categorical definition and you went and you just imported it in. And this is what we're going to call a strict algebra morphism. And you can see that what it means is over on this on the right over here, that that f of a tensor b is equal to f of a tensor f of b. But very often in the world of symmetric monodal categories, right, we don't want equals. What we want is, so like we usually want lax symmetric monodal functors. In particular, we'll want this for our representability theorem. And what lax means is that equality is replaced by a morphism of this signature, satisfying some laws, and also one for the unit, so which looks like this, just to be clear. Satisfying some laws. And so in terms of this diagram over on the left, lax here will mean, well, we want f of a tensor f of b to go into f of a. So we're going to put a 2-cell here, a natural transformation like this, right? And that replaces this with a map, the other way around, with a map this way, right? I.e., we have a map from beta of t of f into f of alpha. And then that acts on the interpretation of any of these formal products in T of A, which is a free symmetric monodal category. Right. And so I can also talk about what a 2-cell is here, right? A 2-cell is going to be a natural transformation so if this is F and this is G and this is phi, a natural transformation like this, such that, well, the so-called obvious diagrams commute. And that, so I will say that if I take this square up here, right, there's sort of 2 obvious ways that I can relate this to that 2-cell down below. I can put it on the bottom, which I will here. Here's G. I can put this here. And this is what we call a pasting diagram. This represents a composite of morphisms ultimately in B. Or I could put it on the other side. All right, where now I have to use TA, TB, and now this one here, I'm going to take to be G, and this one here to be G, because I need the outer boundaries of these things to be the same. This one's TF, and this one's going to be T of phi. This one's phi. And we often call these things, call this F bar, and I'll call this one G bar. So here we would have F bar. And that forms a two category. So this gives us what we call alg lax of T. Algebras and lax morphisms for T. But it's actually very worth noting that sometimes it's important to have strict morphisms. And this is the thing I talked about before in the last one, where sometimes our morphisms represent operations one does, like constructions one has to perform. And sometimes those morphisms represent projections of part of the underlying data of an object, which are generally called displays or display maps. And display maps, right, if you're just projecting out a part of a structure, you expect that to just exactly have the same kind of tensor product. So a display map will generally be strict. So we'll like to also keep around the alg strict T, and we'll include it in here because obviously I could always take the green thing to be an identity, and that would mean that that's exactly what it means for that square to commute strictly is when the green stuff is an identity. So that gives us an inclusion of strict into lax. And it's really understanding alg lax together with this understanding that some of the things will be strict, and in particular the display maps will be interesting and will be strict, that really lets us do our theorem. Okay, so that was one prime. So that was one, and then we did two. Those were both algebras. Now we're going to go back and we're going to do subobject classifiers, and then we're going to generalize them to discrete vibration classifiers, and then we'll have all the tools necessary to even state our theorem, and then we'll claim it, and I'll suggest why it's true, and you can go look up Matteo in my paper if you want to see the details. And that's probably going to get us to the end of the lecture today. It won't be greedy. Okay, so this is algebras and lax morphisms. So now we're going to step back into one categories, and we're going to look at subobject classifiers. Or like, maybe the idea of classification more generally, but really we're just going to focus on subobject classifiers. So the main thing is in the category of sets, in set, we have a special set omega, which is a very fancy name for a set that has two elements, no and yes. Right? A very special set. And there's a reason that this is a special set, because if I have any set A and any subset of A, which I can write via the inclusion, right? Then I can write a function from A into omega, right? Which is is my element in the subset, right? i.e. A maps to yes if A is in the subset and no if A is not in the subset. It answers the question, am I in the subset? And there's sort of a correspondence between these two things. In other words, so what we've seen is that subsets of A, I can produce from a subset of A function from A to omega, right? But now I can go the other way. Suppose I have any function A to omega, which I'll call Q for question, right? This is a yes or no question I'm asking about the elements of omega, because it's a function that takes an element of omega and gives me back either yes or no.
Element of A.
Sorry, yes, an element of A and gives me back an element of omega, which is either yes or no. So here I can put I can put the set yes, including into omega. One thing to notice about this set is that this is in fact a subset of omega, right? Yes, it's a one element set that I've mapped into omega, but it's also a subset of omega. That confluence will fail to be true when we generalize to this whole story to two categories. But right now, right, we have this element, yes, and that determines a subset, which is a singleton set containing yes. And if I form the pullback, right, the pullback here, right, is the set of elements of A in A and yes in yes, right? And let's say Y in A times yes. This is a ridiculous way to write it, but such that, right, this is just a computation of the pullback, such that Q of A is equal to Y, right? That's the usual definition of the actual pullback, right? It's a subset of the product satisfying the equation that the two things in here equal, right? Right? But of course, this is bijective in a sort of obvious way to the set of all A and A such that Q of A equals yes. Because there's only one Y in the set containing yes, it's yes. So we can see that forming the pullback takes the set of things that get yes, right? So I've taken this construction here where I have the subset maps to the question, am I in the subset? And then I have this other one here, which takes a question and maps it to the pullback. Q star of yes. The inverse image of yes. Okay. And those two things, in fact, give a bijection. And not just a bijection, it in fact is if we order no yes then less, then this will be a bijection of an isomorphism of these orderings. Hold on, I won't quite get there. Okay. So why is that a bijection? Well, simply that S is equal to the set of all A and A such that A is in S. And vice versa, Q is equal to the function, so let me just bind an A here. Q of A is equal to yes if Q of A equals yes, and no if Q of A is not equal to yes, which is how we defined this, although I erased it. Okay. So we have this sort of way of taking subsets of A and turning them into functions from A to omega. So in other words, we can say that omega represents subsets. Now, this is the opposite kind of representation that we mostly considered like earlier on in these lectures. We mostly looked at maps out. So this is what we could call contravariantly. In other words, maps into omega represent subsets. Precomposition of maps into omega, corresponds to inverse image of some sets, which is contravariant. Okay, as you can see, A is in a negative position here. It's a contravariant position, and here, well, it's not obvious whether subsets should vary, which way it should vary, but we can take the inverse image. Okay. So now let's see that it's not just set. In fact, if I have any category, we can see that set to the C has an omega 2. By what do I mean by an omega? Well, now omega is not going to be no yes, because this is not a single set, it's a functor. on C. But it's going to have the same universal property. It's going to represent sub-objects. Now, in this case, sub-functors. And a subfunctor is a functor equipped that is sort of with a map, which is at each component a subset. In other words, I can sort of put C into every one of these things, and and then it would work basically. Although of course it's not just going to be yes, but we have a formula for this, which I believe goes back to Levier, but I'm going to write it in a very special way. So I'm going to give another name for this just so that we can always refer to this. I'm just going to call this the Boolean values bool. Okay, omega of C so it's a functor, right? So I'm going to tell you what it does on the objects. So what is it going to be? Well, it's going to be functors from the slice category of C under C to bool. What do I mean by that? Well, bool is going to be a category where no maps to yes, and that's it, by a single map, which we call implication. It's kind of weird to think that no implies yes. This is the principle of explosion in logic. And the reason you assume this in practice, which becomes very apparent if you ever do any formal verification, is that you need to get yourself out of impossible disjuncts. So if you know that it's true that either A is true or B is true, but you also figure out that B can't be true, right? You want to thereby conclude that A is true. And to do that, you really need to be able to say, well, if you want in that case to say that if A is true or B is true and not B is true, then A is true. And so you see that you can define a map out of the disjoint union, you can imply something by checking it on either case. So you're checking it in the A case, of course, A is true, but in the B case, we find a contradiction. We prove that false is true, right? And we need to get out. We need to go and imply anything from that. And so that's why we need the principle of explosion, which as a special case means that no implies yes. So it's a strange convention, but it's necessary, just like having zero be a number is pretty necessary. Okay. Anyway, so what does a functor like this go? This is a functor from a category into a very small category here. Okay. So another way we can say this is these have another names, and in this case it's called a cosiv on C, which is equal to a set of maps. Well, again, like now, remember that bool, we know that it represents subsets in sets, and categories have sets of objects. So we know in particular we're picking some subset of the objects of this slice category. So it's some set of maps F out. But it's a functor, right? So that set, i.e., this means that a map here, right, if sigma is a map of this form, a functor of this form, right, this means that sigma, this is a cosiv is the set of all sets of subsets satisfying this property. Excuse me. Sigma of F is equal to yes, right? So now if I take C and I take F here, now suppose I have a map in the slice category. What does that mean? Well, that means I have this other map like this, and this square commutes. Right? So if this is true, and sigma F is yes, then sigma F prime sorry, I'm writing this in a very confusing way. I'll say it's a set of all subsets of maps out of C, right? Such that if F is in S, then for all F prime, which equals G after S, which is what a morphism in the slice looks like, we also have that F prime is an S, i.e. sigma F prime equals yes. And why is that? Well, sigma G is a map from F to F prime in the slice category. And so sigma G must go from sigma of F to sigma of S prime. But sigma of F we already knew was at yes, and the only map out of yes is to yes. So this is the normal way you'll see this defined. It's an ideal, a left ideal, or yeah, right? Post-composition ideal, something like that, of the category. Okay, so that's what a cosiv is. And this works. This gives you the correct notion of subsheaf. Do I want to run through that? I don't really think I want to run through that. I'll just tell you there's a wonderful book to learn about this, which is Generic Figures and Their Gluings. Things by Reyes's squared, two Reyes's, and one other person whose name I forget. Excuse me. It's a fantastic book that's all about C sets and the math of them. Okay. You can also find this in like any standard text on toposes or anything. Okay. So in other words, for any functor A, right, a map from this to this is a natural transformation, natural in all the C. I didn't tell you how the C's pull back, but if I have a C prime to C, right? Sorry, I need to go forward. If I have a C to C prime, right? Then the obvious thing I would take is I get this sort of evident map. I get a map from C prime sliced down to C. So this thing gives me C prime sliced down to C to C sliced down to C by precomposition. But then I precompose my functions into bool by that, which gives me my map omega C to omega C prime. It's a double dual. Okay. And you can go work out what that means in terms of the sieves yourself. Right, so in other words, I have this map here. I also have yes. Note that constant at yes is perfectly valid in every single one of these, so it still works. And then I have this relationship that the pullback is always given by this.
The map yes down into omega, is that picking up the like the full
cosieve at everything. Yeah, that contains everything. Yeah, the constant map at yes.
Oh.
In the expression as functors into bool,
right.
it's a constant
Yeah.
map at yes. Yeah. Okay. So that is a subobject classifier in a presheaf category. Maybe I should I run through what it is, like how it works, at least how you go from a subfunction. It's believable, of course, that when you pull this back, I get a subsheaf, obviously, because this is a subsheaf of this.
Yeah.
But the other way around, right? Like, what is the map? What would be the map? Blank in S. It's not so obvious, right? Well, we can define it at C. So we have A of C to omega of C, right? We have to do this in S. So if I take an A in here, now I need to take a map out of C, right? A function, map out of C, right? And now I need to give you something in bool, right? Well, what can I do with my A, which lives in AC, and a map out of C goes into C prime? There's sort of an obvious thing, right? Which is I can act on it. Well, I'll write it. Right? I can take A of F. A of F, by the way, goes from A of C to A of C prime. Right? I can act that on A. And then I can ask, is that in S of C prime? And you have to go and check that this works, but this works. Right? So note that this determines a sieve, right? We have to check that that's functorial. Why is that functorial? Well, S is itself a functor. It's a subfunctor of A. So if we did another one of these things, right? If we did a G, right? I'll remind you, we're considering as a map from F to F prime in the thing. Then we would do twice, right? We would do A of G, A of F prime. We need to check that this is a sieve, right? A of F prime of A. We want that to be in A, if this is C prime, of C double of S of C double prime, right? Right. Well, how does that work? Well, this is equal to G after F. So this is equal to A of G after A of F of A, right? Or just A of G of A of F of A, right? But now we know that A of G, right? We know that A of F of A is in S. And we know that S is a subfunctor of this. In other words, we have this naturality square. S of C prime contains into A of C prime. A of G goes from there to A of C double prime, and we have S of C double prime. And this is S of G. We have this naturality square. It's natural transformations, right? So we know that A of F of A lives in here, right? And then if we follow it around here, we get A of G of A of F, right? Of A. But we note that that equals the other way around. So this is S of G of A of F of A, right? And we know that these map to the same thing. In other words, this thing is in this thing, right? That's just what it means to do. It's in the image of it, if you will. And so that shows that this is a set. There's your proof, and you can go and check that this works. Okay. So now we're gonna do 2 prime. We're gonna generalize to discrete op vibration classifiers, which is an unfortunately techno-babbly sounding name. I have to say, I have a pretty high tolerance for technobabble, and I quite like saying it. It's a vice of the category theorist, I think. But the idea is not so crazy. So instead of set, we're going to start with cat. In cat, we have a special category. Set. Yes, set lives in cat. Bool lived in set. Set lives in cat. After you run through this, you realize that we probably should have started this not with sets, but with partially ordered sets to make this really work all the way down. But I'll ignore that for now. So set lives in cat. Okay. And there is an important feature of the category of sets here, which is that there is a notion, right? So I have to say that there is a very special functor into set, which is that we have set, and then we have set pointed, which is the category. Well, you can describe it as the category of the one element set sliced down over set, or in other words, its elements are pairs of a set with an element of that set. And the maps are functions that preserve those elements, right? This, which I'll call U, has a very special property, which is that U inverse of a set S is equal to S, or canonically bijective with S. That actual fact alone tends to it causes an enormous amount of hair pulling in the theory that U inverse of S is not equal to S, but rather just canonically bijective with S. But anyway, you see why? Because U inverse of S is all the sets together with elements whose set is S. So it's just the elements of S. Okay. So now there's also another fun fact that we can use about this is that if I have a function from S to S prime, and I have an element of S, which I can think of as living over it, we've we've actually covered something similar before, but I'm going to do this anyway. Right? There is a way we can lift this, namely I can put S prime here and I can put F of S here. Right? This maps to U, this maps to U, and this maps down to via U, right? Now, this is indeed like a fibration. Last time we saw fibrations, we went backwards. This one goes forwards, hence it is a up fibration, but it is even specialer because you can see that there is no choice of how I make that dotted function, because remember that functions in set bullet or pointed sets must preserve that point. So if I have any map upstairs from S comma little s to S prime comma F of S, it has to send S to S, and it lives over S. In other words, the function is S. Sorry, the function is F. Thank you. Then it just is upstairs already, right? So there exists a unique lift. And this property here, so becomes a definition. We can turn it into a definition. So here, so def, a functor pi from E to B is a discrete up vibration if for all f pi e to b, and yeah, that's it. Excuse me. There exists a unique what we'll lift f e to f lower star of b with pi of lift f equals f. So this is one of these potential red herring cases of namings, because this is not, I did not say that a thing of a discrete op vibration was an op vibration plus an extra property, but it is true that this is equivalent, the theorem, if and only if pi is an op vibration, right? And pi inverse of b is a set of two equivalents. Of categories, I think.
I mean, it has to be literally discrete, right?
It has to be literally discrete. It's a set. Okay, I'll just say it's a set, i.e. discrete category. Yeah, I think that's right. If I did a street discrete vibration, then I would get it up to equivalence, right? If I allowed a comparison isomorphism down in the bottom. Okay. Right. Cool. So now what I'm going to do here is I'm going to say like the correct analog of subset in the category world is a discrete op vibration. And I'm going to talk about that for a little bit. We covered last time, we covered stuff, structure, and properties. A subset is what happens when you take a set and you ask for an extra property, right? A discrete op vibration is what happens when you take a category and you ask for an extra set on it. So it's exactly shifted up one level in the stuff, structure, property stuff. in this category level. So suppose that pi is a discrete op vibration, which theorem, it's an op vibration if and the fibers are sets. Right? So in that case, I can put pi inverse here. And I can put something here. What is that? Well, I just send E to pi inverse of E, pi inverse of pi of E, excuse me, marked at E, because E is, of course, in pi inverse of pi of E. Right? So I'll just write that up, because but of course, here, it's pi inverse of pi of E, and then we put E in there. Right? And that commutes, obviously, by construction. And it is, moreover, a pullback. Why is it a pullback? Well, precisely by this unique lifting property, right? Because to say that it's a pullback means that for every B in here, right, and element of its inverse, there is a unique element of E that lives over B. And that follows by plugging in the identity for F. You see that there's a unique thing living over F, and it has to be the identity. Yeah, thanks. That's why it has to be literally discrete. Okay. Maybe you might wonder, like, is it necessary? So the other thing to note is that, as we saw, U is a discrete op vibration, and one can check that discrete op vibrations are preserved under pullback. So therefore, any pullback of U is pi. So we say that U. So in other words, what we have is discrete op vibrations over B are equivalent to functors from B to set. And we say that U, set bullet to set, is the discrete op vibration classifier. Or, well, sometimes we say that set is the discrete op vibration classifier, but more precisely, it's that U is the discrete op vibration classifier, or the universal discrete op vibration. Okay. Cool. So now we can see that it's not only cat that has discrete op vibration classifiers, other two categories have them too. So this is I learned this from Masiti. Okay. So consider two cat, like if consider cat to the C. Now cat C can be a two category or it can be a category. It doesn't matter for this. Let's just take it to be a category. That's all we're ever going to use, and it's easier. Then this has omega. And the omega is defined very, very, very similarly to how it was defined in the set case. Right? Which is to say, now we're going to take two category functors from C sliced over C to set. Again, C sliced over C could, a priori, is a two category. But if C is a category, of course, then it's a category.
This is cat to the C.
No, I'm thinking cat to the C, and I'm mapping out of the C. If I did cat to the C op, I would have to put C sliced over little c. Inward sieves. Sieves. This is co-sieves.
Oh.
It's a conventional choice. It's the exact same formula as this up here, but just one level up, where I've substituted bool or prop. Bool is properties.
Right, but didn't we get this property where we've got map from C to C prime? It's giving us the map.
Omega C to omega C prime.
Oh, right. Yeah.
Because it's a double contravariant. Yeah. And similarly up here. All right. And this with the exact same kind of functoriality. This is well, this, and then we can, of course, I need to tell you what omega dot C is. I didn't tell you what this is in the decategorified case, but it did produce yes. But it's very obvious. You just go into set dot. I will tell you that if you think of propositions as sets containing at most one element, right? In other words, you replace bool, which we call the set of yes, no, with the set of subsets of a one element set direct, like, which correspond to yes or no, which is to say the empty set or the one element set, the power set of a one element set, then you get the fact that pointed propositions are yes. Yes is the only pointed proposition for one element set. So this is a very direct categorification of the subobject classifier in this sense. However, you know, there's another way to do this for two categories, which I guess I just won't go into, where you can see the remember, like it's worth noting that we got this set pointed, and this one also you can see as a comma of a point. So there's a sense in which it just so happens that when you take the comma over the inclusion of yes in the poset thing, you end up with something which is still terminal, but in this case, you generate something wholly new. Anyway, I won't go into that. Right, so we have our universal map, and that universal map is induced by post-composition by the universal map in cat, as you can see. Okay. Right, so this is a discrete up-vibration classifier. Okay. So now we can come to the main theorem. Oh, so let me compute one of these for you. I think it's worthwhile. Remember that the underlying data we were considering before was e.g. C is equal to this category shape, which we, you know. I'm going to write interface again. This is the same object as the other one. This shape, which was the underlying data of one of our modules of systems, right? When we map that into cat, we pick out a category of systems, a category of interfaces, a category of interactions, and these two maps from interactions to interfaces, giving the input and output interface, and the map from the category systems to the category of interfaces projecting out the interface. All of these are supposed to be understood as display maps. Right? They're just projections of typing information. Okay, anyway. Right, so e.g., let's compute omega of cat to the C, because it's going to come up later. Really, I mean, technically it's like that. Okay, so let's just start. Let's start with interface. Right? So, well, I'll put it out. What it's going to be, first of all, is it's going to be something that looks like this. Right? Because it's an object of that category. So let's just compute these in a row. Omega cis. It equals functors. Two functors, but the domain's just a category, so. From cis sliced over C to set. What is cis sliced over C? Right? Well, cis sliced over C, we have two maps out of C, out of cis, right? We have cis, the identity, and we have cis to interface, right? These are our two objects of this thing. And we have a single map from one to the other, which is post-composition by cis to interface, which does take the identity to the interface. That's it. Those are the only maps out of cis. So we see that we get functors like this into set. In other words, that is equal to set arrow. Right? Okay, let's compute omega interface. Again, by definition, it's interface sliced over C into set, and then we just compute what interface sliced over C is. In this case, it's very easy because interface has no maps out of it, except for the identity, of course. So this is a singleton set. So we end up with just a category of sets. Now, before we do anything, right, let's figure out what is the map from omega cis to omega interface, because I can start by slowly replacing this here. We've computed them to be set arrow, and we've computed this to be set and this to be set. Or I'll just go through the whole thing and then we'll do all the maps. How about? All right, and now we do omega interaction. Again, it's defined by the formula, and then we compute. What is the slice of interaction over C? Well, there's two maps out of interaction other than the identity, right? So we have interaction equals interaction. We have interaction to interface. This is the source, and the interaction to interface equals the target. They both her face. Excuse me. And then, right, these are all objects of the slice. And then there's two maps, namely the identity always maps into everything else. There's no maps for relating the two ones to interface. So we end up with that into set, which we could write like this. That's span shapes, right? So we're putting this here. Now, I think you can guess what these functors are between everything here, but I want to compute it. So let's say we take the map from cis to interface, and then we should get a map from omega of cis to omega of interface. And remember that what it is the double dual, as in you precompose and then you precompose. So, right? Is this making sense? We go from cis to interface, right? Yeah, am I doing this right? Interface to cis. Yeah. We go from cis to interface. So this gives us a map from the slice of interface. Remember, we do this in two steps. We take, so I'm going to compute now this, right? So I'll move this down here, give myself a little more room, right? So we take the map omega cis to omega interface is going to be given by, well, we take our map cis to interface, right? And then that gives us a map from interface over C to cis over C. Now, these are very small categories, so we can compute it out. In particular, interface over C is just interface equals interface. And cis over C is cis equals cis and cis to interface. And the map between them, right? Now, when I precompose interface equals interface by cis to interface, I get, so this one object goes here, right? In other words, I'm going to draw them out more abstractly. The map is this one, right? But that's not enough. Now we precompose by that. So we take our remember that cis we computed was arrows and set, and interface was just sets, which corresponded to the function from interface. So now if I have a functor from this into set, I precompose and I get a functor from this into set. What does it do? It's taking the codomain. So this is codomain. Now, I want to stop and remind you, at some previous point in this lecture series, we covered variable sharing doctrine. You remember what I told you about the variable sharing doctrine? It was that a system in the variable sharing doctrine was a set of behaviors, or in Jan Willem's behavioral control theory, was a set of behaviors. Boy, I hope I did actually cover this. But it was a set of behaviors. And then a set, its interface was a set of variable values. And a system was that set of behaviors and a projection into the set of interval values, right? In other words, in the variable sharing doctrine, we had a set of behaviors. A system is a set of behaviors together with some exposed variables. An interface was that set of variables. And the way that the systems lived over the interfaces was by projecting out that set of variables. And we've just discovered that again here. Let's keep going. So, I don't know how much I want to keep going, but like you can see that if you compute this out, right, by the same formula, if I look at the map from interaction to interface, right, which is given by one of these maps, then precomposing by the one from interface to interface, which of course is only the identity, gives me that map again, which means that and that map lived at the corners here, right? This one, if I go down, we have the identity on interactions, and then we have the two maps to interfaces down here at the feet. And so when we precompose by each of these maps, we take this thing and we give ourselves this thing or the other one. And so these are the restrictions of the feet. In other words, this here is the underlying graph of categories that underlies the double category of spans. Right? Okay, so that is how the variable sharing doctrine worked. They composed by taking pullbacks and spans. We covered that. So what's really beautiful here is what we're seeing is that Jan Willems was at something really fundamental with his variable sharing behavioral doctrine. He's getting at the discrete out-vibration classifier. But we're not quite there yet, right? Because there's an important thing. It's like, how do we know? Okay, so this is the graph, right? This is the underlying data of that systems theory, but this is not the systems theory. I haven't told you how systems actually interact via the interactions. But I claim that we can deduce it just by knowing that this is the discrete out-vibration classifier. And a few properties about our monad for systems theories. So I'm going to say this. We have claim. We have a two monad, T, on the underlying data for systems theories, such that alg lax of T is symmetric monodal loose right modules plus lax morphisms. A lax morphism is, lax on the lax functor on the double category. It's lax on the and it's lax on the interactions, right? Somewhere up here, it's a bad choice because God knows when I'm going to stop flicking through these. But somewhere up here, we've already seen this happen with our behaviors. Yeah. Right? Remember, when we looked at the compositionality of behaviors a few lectures ago, we noticed that we have this kind of compositionality, which you can see looks like lax. I mean, we're taking this thing and this thing, right? Maybe mention it's lax. So the kind of morphisms that's important for this is going to be the lax one, right? I'm going to take this as given. I hope that the discussion of the symmetric monodal case convinces you that you could do this, right? And then I'm also going to take plus a few properties, which is one. Let's just start with one, and we'll add some more. One is T preserves discrete op vibrations. And pullbacks of discrete op vibrations. Now, I'll tell you this, that all of these properties are going to be implied by whatever they are going to be implied by T is familial, if you know what that is. So another way of saying what I'm about to say is that there's going to be a familial two monad on this, which I think if you know about familial two monads and why they were invented and looked at, and you can totally believe. For example, symmetric monodal categories, free monad is familial. Yeah, so might as well just say it's familial. But it implies these properties, and these properties are quite useful. Let's just see what happens if we take this for granted. We take it 1. So now, what I want to do is I want to discover the systems theory structure on omega, which, as we saw, was very like omega. Remember, it looked like this. It was what we called before span set 1 comma dash on span set. Like that's what we just computed. That at least that's the underlying graph it is that. Okay. So what does that mean? Well, that means I'm going to try to compute T omega to omega some algebra, which we'll call little omega. Now, this map is a map into omega, right? And omega is defined, we came to it by its universal mapping property, namely that maps into it correspond to discrete op vibrations. So for this to work, right, any map like that is determined by the pullback of this thing. Right? Let me suppose that this pullback is this one. As in, let me just take, remember I said that T preserves discrete op vibration, so TU is certainly a discrete op vibration. And therefore, there is a unique omega, well, unique up isomorphism, which classifies it in this way. And this I'll call omega dot. It is also true that because U is a discrete op vibration, if I show that omega is an algebra, omega dot will also be an algebra. We can just sort of pull back the equations up to omega dot. Okay. What is omega, right? So remember that what happens in T, right? These are formal composites of systems and interactions. And omega takes a formal composite and gives us the actual composite. Okay. So what does that do? Like omega, so let me take the formal composite of S dot I. Now remember, what is S? S, really what I'm taking is a formal composite of S to I naught to I1, right? Because that's what a this is what a what this shape looks like in the systems theory, right? This is a formal composite, but I'm telling you I can compute it, and I compute it by the classifying property. By definition, this is T inverse, T of U inverse of this formal composite, right? Now, what does that mean? Well, remember, U just forgets the pointing, right? of the sets involved in all these things, right? So in other words, T of U inverse is something, I have this diagram here, and then over it, I'm going to put an element, right? I'm taking the sets of these elements, right? And they all have to map to each other because the maps are all pointed, right? So this is equal to the set of all those elements up there where they are all in the appropriate thing labeled below. And they all map to each other under these things, right? Well, note, right, that I naught is determined bijectively by I, right? And I naught, this is I1. I1 is determined bijectively by I naught would be determined bijectively by I if it weren't constrained otherwise by S. So this is bijective to the set of pairs S comma I, S is in S, I is in I, such that if I call this, E and I call this L or something, such that ES is equal to LI. That's the pullback, i.e., this is S I naught, this is the pullback, right? Oh, and what is its outer one? Like, what does it project down to? It's still this, right? So this is this thing here. This is omega of that formal composite, which is what it was supposed to be for the variable sharing doctrine. So you see that we've discovered Jan Willem's variable sharing doctrine, Jan Willem's behavioral approach to control theory, by looking for a discrete off vibration classifier. I won't, I think I'm going to ignore the rest of these. The rest of these are important. I didn't check that this was actually an algebra, you see. You start needing the other assumptions to check that it's an algebra. But again, it's all implied by familiarity. And familial essentially means that there are string diagrams that describe your kind of composition, or like pasting diagrams for your kind of composition. That's basically what familial means. It's not a hard thing to hit. I think I could suggest how to do this, but I think I'm just going to leave it as something that is it's work to write it down. It's not particularly enlightening, and all we're going to use is that you could do it. So that's my feeling on it. Although I do think it's actually I do think it's enlightening to actually write it down, but sort of just it's not necessary for the systems theory. I just think as a category theorist, it's very pleasant to actually have very concrete constructions of these things to understand what's really going on. Talking to Jason here, where we have a plan to do this. So, so it's not that I don't care. It's just that it's not necessary for us in this story. I'd rather move on to the actual systems theory stuff. So now I can say our main theorem.
Sorry, I do have a quick question. Is there a nice analog for this in for sub-object classifiers where you get if you've got a nice monad on a category, that the sub-object classifier inherits an algebra structure for the monad?
Yes, if you work with posets. So if you think about what happens, let me give the theorem, and then I'll decategorify it for you. So okay, if I'll present it like this: if T k to k satisfies my assumptions, and e.g. is familial, Then and K and omega is or like, let me just say that this U omega dot to omega is a disk op vibration for K. Then I don't know how I want to be about this. It's really like the strictness things are so annoying. If if it's flexible, how about I just say this, right? That yeah, and is flexible, which I won't say what it is, but it's any good categorical theory is flexible. It means that you don't add equalities between objects. You only add equalities between morphisms. So note that when you do a symmetric monodal category and you add all these associators and stuff, you don't actually add equalities between the objects. The laws are governed by morphisms. Then composites of those morphisms can be equal. And that makes you flexible. So I'm just going to say that because that lets me give a simpler form of this theorem. Otherwise, it's not, none of this is essential. It's just as I mentioned, my hemming and hawing here comes down to this thing I mentioned up here, right, which is that this is only a bijection. If that were an equality, you'd get a lot easier. Your work would be a lot easier for you. Right. Yeah. In general, you constantly have to wriggle. Technically, you only get a pseudo algebra. And then you have to strictify the pseudo algebra into a strict algebra. But if you're flexible, you already could do that. So,
is it so before you define the two monad whose strict algebras are symmetric monodal categories?
Yeah.
Where there's also, I guess, another two monad whose pseudo algebras are symmetric, but whose strict algebras are strict.
Yeah.
Isn't flexible because you don't have.
Yes. And in that case, you don't. I'll run through what this theorem applies to both of those monads, and I'll run through what happens when you apply it to them because it's a good case. So, I mean, I'm not saying the theorem in full, but the theorem, like, I would give you a pseudo algebra structure, but I haven't covered it in these lectures. So I'm going to give you the strict version. But if you believe me about the pseudo version, I can tell you what happened. It's pretty simple in that case to see why this works. But then omega has the structure of a T algebra, and for which U is a strict homomorphism, a strict Cartesian homomorphism. And what that means is simply that we have we have T omega dot to omega dot, omega dot, T omega, omega, U, T U, omega, pull back. 1 and 2, U, which we might think of as omega dot to omega now, classifies strict discrete op vibrations in alg lax T. And this strict here is one thing to think about is that these discrete op vibrations are display maps. Their fibers are sets. You can think about them as generally projecting out some set of stuff, some set of structure, right? Their fibers are sets, so they are like you've taken something in the base and you've added a set level more of data to it. You've added an element of a set to it. An element of a set to it, which would be adding structure. So it being strict here is saying that that the algebraic structure, the two algebraic structure, which is really algebraic stuff, but whatever. The two algebraic structure that you put on these things is projected out directly. So let me look at this. E.g., so we're gonna come back to this for system series, but for now, let me say like e.g., if we have T equals SMC monad cat to cap, and that is flexible, and we get this theorem. We have set bullet to set U, right? And we have T set bullet T set omega dot TU, pull back. And you might say, okay, well, I put a symmetric monodal. Omega just says that set is a symmetric monodal category. But which symmetric monodal category? Well, it is determined by this in the same way we computed it last time, right? Omega of A tensor B, right? The formal composite, A tensor B. Well, by definition, it is, or by the classification property, it's TU inverse of A tensor B. Right? Which is, in other words, the set of all A, comma A tensor B, comma B, formal composites, right? i.e., it is the set of all A in A, B in B, or A times B. So set is a symmetric monodal category with times. What does that's one. Now two says that if we have E to B, where both of these are symmetric monodal and pi is strict, then there is an essentially unique map S to set, which is going to be pi inverse. Spoiler, I mean, it's the same one, right? Maybe I could say this. It classifies strict discrete op vibrations, and the forgetful functor from algebras to the thing sends it to the same. It classifies it in the same way. And there's a thing you can check, which is that if T satisfies our assumptions, which again I haven't told you, but in particular if it's familial, then being a strict discrete op vibration in Alge-Lax is in fact just being a strict morphism in Alge-Lax whose underlying map is a discrete op vibration, which means that it's significantly easier to check because you check. Oops. Oh no. Hello. Do I have to share again? I think so. All right, sorry about that. Technical difficulties. Okay. Right. So you can separate out your algebra structure. You check that it satisfies the algebra structure, preserves it, and that then you can check that on the underlying thing it's a discrete op vibration. So that's actually quite nice. That is going to be knowing that makes it quite useful for when we check what discrete op vibrations of system series is, because a priori that could be crazy, but it turns out it's not. It's just a strict morphism of system series where every functor involved in that is a discrete op vibration. So that's not that hard to check. Okay. Set dot, and we have this map here that is a pullback again, U dot. But now everything here, well, this thing here, pi inverse here is only lax. So we have pi inverse of E times, right? Because we're going to set times pi inverse of E prime 2 pi inverse of, oh, sorry, these should not be B's, they're B's. And what is this map? What is this laxator? Well, here is an E that maps to B, and here's an E prime that maps to B prime. And there's a very obvious thing we can do to them, which is we can tensor them. And that maps to, well, by the very assumption that pi was strict, this maps to B tensor B prime. So you see that it's quite necessary that we do that. In fact, it is this that is our laxity is the monoidal structure on the fibers that compiles together to get this, which there is only a monoidal structure on the fibers of a map if it's a strict morphism. If it's lax, you don't necessarily have this structure in the fibers. Okay. So that's this example. To bring it back to the little sidebar we were having, if T was in fact the free strict monoidal category monad, right? Whose pseudo-algebras are monoidal categories. I don't think, by the way, that symmetric monoidal categories are pseudo-algebras for anything. Strict. Except for themselves, of course. As in, you know what I mean? Because there's no strictification theorem for
symmetric monodal.
Yeah.
Can you not strictify symmetric monodal to a strictly monodal symmetric monodal? Yeah. So not like
you can strictify everything but the symmetry.
I believe that. Right.
What am I saying? Oh, okay. This has confused me a little. I apologize. Let me just say the thing I was going to say. If you just forget about the symmetry for a second because it's confusing me. If we take strict monoid monad on cat, its pseudo-algebras are a form of symmetric monoidal category.
A form of monoidal.
Sorry, a form of monoidal category. Thank you. That's a form of monoidal category. And what you can see is that set is not a strict monoidal category under times. But as you see, we had no choice of what to make for the algebra structure of set. It has to be Cartesian product.
Yeah.
So we only get a pseudo-algebra.
Yeah.
In general, we only get a pseudo-algebra. But if your monad is flexible, you can then replace it. And that's what happens if you already took monoidal algebra monad.
Yeah.
Any pseudo-algebra for the monoidal category monad is in fact equivalent to a strict one. Because you can fold in all the extra isomorphisms into the structure isomorphisms that are already put in. So that's where flexibility happens. And so I guess I should add to my assumptions that that the monad for system series is flexible. You have a flexible. Which, again, if you look at our definition if you believe what I say about flexibility, that it means you don't add equations between objects in your algebraic theory of categories, right? We didn't do that for our system theory. We only added isomorphisms. Yeah. So we should absolutely be flexible. Okay, so that's what we do there. Now, right, if T equals the free symmetric monoidal loose right module on our underlying data for such things, right? Then we've computed that omega is equal to span set 1 comma dash acting on being a module for span set, right? And what then is this representability thing here? What then is this this universal property? Well, maybe I should say, sorry, let me just like write out what this would be. If I have I have some kind of here now I have some kind of systems theory. I'll call it you know, SI, right? And over it we have some kind of discretely fibered systems theory. Right? So this is corresponding just to E over B. Right? What does it mean to say that this is discretely fibered? Again, it means that we have maps all the way down, right? They preserve the strict system series structure strictly, and each one of the functors involved is a discrete op vibration. So the way to think of this is that S tilde is just an object in it is as a system together with some element of some extra set of that system that varies covariantly. And what do you know? If you believe that that's true, maybe it's not too weird to believe that from this we get our thing that runs horizontally in that page, but I'm going to write it like this. S pi span set dash over span set. We get a map here, right? Which is, if this is pi, then this is pi inverse. Right, and those are both lax. So this part is exactly going to be Bob Paret's lax representables for the tight representables for double categories. So if you know about double category theory, you know that the representables are lax functors into span set, and we've recovered that here. But then we also add the system stuff over it. So I think next time I will work out what this means for representable behaviors. Because right now, what I've showed you is that if you can compute some of these discrete fibrations, you can get these lax functors into the Jan-Willems behavioral theory with no time variation, but that seems to just be pushing around the definition, right? I now need to compute some of these for you out of actual clock systems, and then we'll get our full taking behaviors to be maps out of clocks. We'll get our representability compositionality theorem in complete generality. And then we'll work out all the examples we can of that.
Right.
Thank you.